well, we thought there was about time that there's a vast body of literature documenting potential mechanisms that might affect predictability on decadal scales, which are not occurring into the environmental, in the oceanic environment. And such a vast body of literature is there, and we thought it was a good idea, it would have been a good idea to make a review, sort of white paper documenting how we can exploit the potential embedded in these non-oceanic components in the prospects of fully exploit their potential into future decadal prediction systems. A major focus in CIMIP 5, and this certainly is going to be a major focus for the next CIMIP, is the ocean, and there are good reasons, obvious reasons as to why this is so. But the level of complexity of Earth system models is clearly growing with time, and certainly there's a lot of potential embedded in the other components which we haven't yet even started to explore, or we are just starting now to explore. And now the question is, how can we fully explore these additional sources of predictive skill that is there, and we may be able in the future to dig it out in a better way. So we decided to focus on a number of specific subsystems of the climate system, including sea ice, land surface, stratosphere, and aerosols, as the most suitable candidates to be somehow to be explored in this study. And so we decided to focus on these elements. And the time is short, and the kind of literature is very vast, so I will sort of squeeze, try to be within the time, and I will pick up only a few highlights, a few examples, and possibly I try to also to emphasize what are the challenges that we are facing, especially if we think we want to make the most and maximize the potential predictability associated with these components in the decadal prediction system. What are the issues that we need to face? So starting with the sea ice. Sea ice predictability has been mainly explored using potential predictability approach. This is a study from Torben Koenig and colleagues from SMHI, exploring the potential predictability using prognostic potential predictability approach. And this study was showing, it came out a few years ago, was showing that not only the sea ice state is predictable in state, particularly around the sea ice ages and in the Arctic, but there was a number of other additional climate state variables that might benefit from, that show a consistent pattern of predictive, potential predictability, particularly the surface temperature and the precipitation. So this is pointing to the fact that the sea ice, sea ice cover predictability, in this case this is sea ice thickness actually, but the sea ice state's predictability is not just beneficial for, potentially constraining the sea ice state in the initial value sort of hindcast might be beneficial not only for the sea ice state itself, but clearly this is going to affect a number of other related processes, and there might be benefits from both the atmosphere and the ocean. Talking about the ocean, this is a cartoon from Schmidt showing a well-known phenomenon occurring in the high latitude in the North Atlantic, related to the propagation of great salinity anomalies. This is a kind of well-documented phenomenon that involved the sea ice export through the Franz Strait, and that eventually propagates through the Greenland Eastern Current and then reaching the Labrador Sea, and finally, ultimately affecting deep convection and deep water formation and meridional overturning circulation. This is a kind of phenomenon that, being able to somehow predict freshwater pulses coming from the Arctic it will be incredibly beneficial. Not only for the predictive skill, would benefit from the indirect effect on the oceanic system as well. And of course, the literature, and particularly this work by Belkin, is documenting how changes are very large correlated changes in the surface temperature occurred as a consequence of the transit of these great salinity anomalies in the temperature and salinity of the Labrador Sea. So this is just an example, and it is showing the potential, what are the potential benefits from better constraining the sea ice state for the ocean environment, of course, but there's also an enormous body of literature documenting possible interaction between Arctic sea ice changes and the switches in the phase of the Arctic or North Atlantic oscillation. This is an old paper by Berenice and Silvia Vinegas showing or describing, illustrating a possible interplay between particular sea ice extent changes in the marginal seas around the Arctic Sea and the changes in the Arctic oscillation, and this is a kind of mechanism fitting very well into 10 to 15 years Arctic mode oscillation. There's also a number of other works which try to connect Arctic sea ice and mid-latitude atmospheric variability connection, although there's lots of discussion going on this controversial kind of topic, but there are studies which try to tackle this issue and whether there's any relationship linking together the rapid Arctic sea ice decline and a recent chain of extreme winters and summers in the mid-latitudes. So what are the issues with the sea ice? In exploring sea ice predictability, in particular in initializing the sea ice, of course there's a big limitation is assessing sea ice prediction skill is the lack of observations, and we know we can only rely on a relatively short record, particularly starting from the 80s onward, from the satellite ages. And that's clearly a fundamental limitation which is not affecting only sea ice but also other components of the climate system. But another issue is the physical consistency among the sea ice, atmosphere and the ocean initial states. If we want to properly initialize a coupled system, we need to take care of a well-balanced initialization, and we need to take care that all these components are somehow consistently initialized with each other in order to reduce the impact of possible shocks after initialization, which would have a detrimental effect on the forecast skill. And of course, most of the studies are focusing on the Arctic, but there's a lot of going on also in the Southern Ocean, and Southern Ocean has been very poorly investigated under this point of view, and that might be interesting also to go there. Land surface, this is a topic that we mainly struggle with in looking for literature which was documenting the impact of land surface on the multi-decadal or decadal timescale. I mean, most of the literature connecting land surface and predictability deals with the seasonal timescale, as we know. There's a lot of studies have been done. Not much has been done in terms of trying to explore what kind of relationship is between land surface processes and the multi-year or decadal scale variability and predictability. This is a picture showing something that we've been mentioning yesterday many times during other speakers' talk, and how the anomaly correlations does dramatically reduces after we remove a trend over, and this is particularly also over land. This is just anomaly correlation based on a number of European systems, decadal prediction systems based on the combined project experiments. And this is certainly something that we want to explore more. I mean, we expect that most of the, in this kind of experiment, the skill is expected to come from the ocean initialization. Now the question is whether we can improve the land skill by perhaps making a better use of the land surface state, either by initialization or by a better representation of the land surface atmospheric interaction. Again, this is something that will be enormously beneficial for predicting things like multi-year droughts, particularly like this is just an example showing the well-known Dust Bowl drought during the 30s. Now, there are interesting studies pointing to the key role played by land-atmosphere feedback, particularly over the US Great Plains. This is a work by Siegfried Schubert and co-workers quite a few years ago, and showing how the multi-year or multi-decadal changes in the hydrological cycle over the US plains is very strongly affected by the representation and the inclusion of land-atmosphere coupling effects. And this picture in particular was showing how enabling or disabling and switching on and off the land-atmosphere coupling that's basically have a key impact on representing the multi-decadal variability in the hydrological cycle, particularly over this US Great Plain case study. Another aspect which is really pioneering, and so it's not surprising that there's very little literature on that, is the role of dynamic vegetation. This is a work by Martina Weiss and co-workers by KNMI, showing they made a number of hindcasts, initialized hindcasts, using a model which includes a dynamic vegetation model in it, and targeting specifically what is the role of vegetation in the decadal scale. This is, I think, this is the only work that I know of at the moment which is specifically targeting this particular aspect. But I mean, certainly there is some other work going on in the meanwhile. At the time, that was the one that we were aware of. This picture is showing in particular what are they made some control experiments to contrast what is the scale by including or excluding the dynamic vegetation. And wherever you see red, they found that the probabilistic scale score improves as an effect of including vegetation wherever you see red. And this is particularly true after 1 year after initialization, whereas clearly scale decreases with time when you move away from the first year. But there is some impact. Of course, there are shadows and lights, and there are also regions where there is a deterioration of the scale. Wherever you see gray is identifying areas where having a dynamic vegetation can locally decrease the scale. But there are, as I say, after 1 year after the initialization, there are certainly more red areas, and particularly in the northern hemisphere. Here, there is an interesting point, is that in order to explore the added value of vegetation, someone should wonder whether initializing in November is the best time of the year to do so, particularly in the northern hemisphere. This is what CMIP-5 protocol prescribes, but someone should wonder, probably the initial vegetation state in early northern hemisphere spring contains a lot more useful information in order to better exploit the impact of vegetation on scale, on decadal scale. And there are also studies which tackle the predictability associated with things like deforestation, like predictable trends in deforestation may provide a source of predictability of those areas which are affected by deforestation. The stratosphere is certainly one of the most promising frontiers in decadal prediction. There's a lot of multi-year or up to multi-decadal variability going on in the stratosphere, and quasi-biennial oscillation and sudden stratospheric warming are the two processes that most outstandingly show some clear quasi-biennial oscillation per se is a sort of very regular sort of cycle affecting the tropical stratosphere. Sudden stratospheric warmings show some very low frequency changes, like there are epochs during which there are more sudden stratospheric warming compared to others. Clearly, sudden stratospheric warmings are not predictable per se, but including a stratosphere in a model which is capable of representing this kind of feature might be beneficial for including predictability in the system. But there has been, related to quasi-biennial oscillation, there have been studies that show how initialization of the tropical stratosphere can be beneficial for representing the correct phase and the amplitude of the QBO for a few years. This is particularly studied by Adam Skyfe and co-workers, comparing the two systems here, the UK Met Office and the Max Planck Institute, and it's showing that there is a skill for quite a few years after initialization, that the correlation is quite high after initialization. So certainly, but the point for initializing QBO is not just because the QBO is predictable, it is sort of expected by, but there are other interesting aspects related to the initialization of the QBO, and that has to do with the teleconnection of the QBO with the exotropics. The QBO skill may potentially impact predictability also of the surface wind climate in the exotropics through the Holton-Town relationship. We know that there are connection between the tropics and the exotropics, and between the QBO and the polar vortex activities. And so this is a very interesting avenue that should be explored, because initializing QBO would be beneficial not only for the stratosphere itself, but also for the climate, the surface climate in the exotropical regions. And this has been really poorly explored. I mean, this is perhaps one of the few studies that consider this kind of aspect, and I think this is something that we should look at with more attention. There's a number of studies also showing how the stratosphere, troposphere, ocean sort of coupling might be potentially lead to decadal predictability. This is famous work by Reichler, appeared on Nature a few years ago, and showing how there has been, this is the model results, it's based on GFDL model, and it is showing how there are coordinated changes connecting the stratosphere through the troposphere and the ocean, and finally impacting the ocean and the meridional overturning circulation, changes in the temperature down to 1,000 meters. And so there is a very interesting connection linking the very high layers of the atmosphere, the middle atmosphere, down to the deeper ocean. Again, this is one kind of process that would enormously benefit from including a stratosphere in a coupled system, and explicitly including this kind of phenomena. And the 11-year cycle is yet another very important topic. And there's there has been a lot of literature on this in particular, connected to the predictability. And there are two basic mechanisms. We know that the presence of a stratosphere in a coupled climate system would allow not only to represent the known bottom-up mechanism. We know that total solar irradiance is affecting sea surface temperature and heat content in the ocean. This is the bottom-up mechanism by which the solar cycle can impact on decadal predictability in the ocean. But there is also the top-down mechanism through which the solar variability can impact the climate variability. But in order to exploit this aspect, we need a stratosphere resolving model with a proper stratosphere in it, and so that the ultraviolet part of the solar spectrum and its interaction with the ozone in the stratosphere can be represented. So this is another aspect pointing to the need for having a better representation of the stratosphere even in decadal climate forecast context. I will be very, very quick on aerosol. Here, the big issue with the aerosols is that there is a vast diversity across models. There are models which feature very different model-to-model differences in terms of radiative forcing associated with the anthropogenic aerosols. So now the issue here, how do we deal with this big, model-to-model uncertainty? This is one particular result based on Hadgem model showing how the aerosol can impact on the tropical storms, particularly switching from one type of scenario simulation, whether we include a very strong mitigation or a weakly mitigation scenario, the change in the number of tropical storms expected for the next decade has changed quite dramatically. Now the question is, if we move away from a hard gem and we use another model that, I don't know, I'm not aware of other studies tackling this kind of issue, but I mean, it is to be expected that this is a very model-dependent feature. So the trouble here, oh, this is not working, okay. So the trouble here is how do we deal with this model-to-model diversity? There are models which have a very weak radiative forcing associated with aerosol, and there are models which have a very strong radiative forcing, and of course their response to changes in their aerosols is going to be also very different. So I'll skip this one and I'm going to the end. So it is clear that there's a number of including additional subsystems or better representing other systems than the ones that we currently make use of is certainly beneficial. And in our traditional approach, initialization and boundary forcing are the two kind of sources of predictability, and clearly this, for people working in decadal forecast, we want to maximize the first kind of predictability, of course, because that is what is the added value compared to the long-term projection. There is certainly a role played by other systems which are not necessarily initialized by simply the buffering of the information which is nudged into the initial state. Is propagated through the system, and including or not including a given process will have an impact on predictability, regardless of whether or not we are capable of initializing this specific component. So there's certainly something to work on in the simple, even uninitialized part of the decadal forecast system. Without willing to be, upsetting too much at the Lawrence, but I think it's certainly next generation system of a climate forecast system should try to maximize at most what is the impact of the non-initialized components. The simple representation of processes will certainly add one additional leg to the scale balance of decadal forecast system. So I think that.
Thank you. Questions? Yes.
Yeah. Do you know what is the sort of a memory time scale of the vegetation components?
It's a very difficult question. You mean it's the memory? Well, I don't have a specific answer to this question.
Yeah.
It's a very, very specific question. I mean, but I'm sure that Martina and Bart van der Hoorke will answer to your question. I mean, what I can tell, there is an effect in the very short time scale. Certainly, I'm not expecting vegetation is going to affect the very long lead forecast scale, but it certainly does have an effect in a very, very few months after. But even a year, it will be. I mean, I think it would be an improvement.
I think it's really great that you emphasize the stratosphere, and I'm, as a stratospheric person, I can only support this. But what I would like to point out is that there is in the frame of CMIP, there is a stratospheric diagnostic project called DynVar, and they need for their analysis some variables. And it's just to write out something or to say for a couple of months daily or hourly values so that they can use it post-processing. And I think one should take this into account, and maybe that also the decadal simulation could be used by the DynVar community for their analysis. So in advance, that one think about to write out some more diagnostic if possible, or if one has the chance to do it.
Well, we have had, we have had interaction with DynVar. They've come up with some suggestions, but they're not quite as elaborate as that. So it's more on the lines of monthly kinds of data rather than daily and so forth. But that could be perhaps revisited or something. Okay. Other questions? Yes.
Can you just clarify exactly what an ecosystem buffering?
Yeah. Well, this is simply the signal which is carried around by individual components of the climate system. To explore this better, I can go back to the very initial slide on great salinity or this one. We think about this is a very hyper-simplified view of the climate system as a sort of web or chain of different subsystems which are connected to each other by a number of feedbacks and processes. In this particular case, predictability is coming from, for example, the propagation of fresh water or ice through the Fram Strait into the ocean. Now, regardless of whether or not the ocean is initialized, and we know it is, but even if it was not, as a simple signal carrier, it will, contribute to predictability of the system. I can make another example. I'm thinking about Stanchikov's study about how the volcanic impact or volcanic signature is carried forward by the ocean. The ocean is there playing a role as a sort of system buffering, is not being initialized necessarily. Even in a forced experiment, you would have this kind of predictability in a way. So what I'm trying to emphasize with system buffering is a simple fact that there are non-initialized components. We will still, by the simple fact that they propagate the signal, which is into the initial state. All the predictability is in initialization, we know this. But by including or not including specific key processes that may or may not be in the system, like, for example, there are systems which do not include the stratosphere. And what is the impact of not including the stratosphere? This goes back to the top-down mechanism that I was mentioning before. The exclusion, if you like, of one specific component could be detrimental for the skill. If we include this particular, the stratosphere may act as a buffer in a way. It doesn't necessarily be initialized. In the study of Adam Skive, it is investigated what is the impact of initializing the stratosphere. But even if you don't initialize, it will still be part of the system and will contribute to, by better representing given processes, will contribute to predictive skill. So I don't know if.
Okay, Eric and then John.
Yeah, just to follow on that point, I'm not sure. Is it because we don't initialize the stratosphere that it becomes an element to be taken into account? Imagine you have a system where you initialize everything,
right?
Then you wouldn't have that problem. So I don't understand why it's a third.
Well, the stratosphere
I don't understand why it's a third branch. Is that because you're not doing one branch properly, or?
Yeah, it's both. Either you this is a number of different issues, and we should look at each one individually. The stratosphere can be initialized, so perhaps it's not. But there are other components that in the next few years we may not be able to initialize. I'm thinking about real-time predictions and land surface. How do you initialize land surface in a real-time forecast system? Do we have a network which allows us to have daily values of land surface globally? I don't think so. In the next few years, we will keep on not being able to initialize the system. Yet, by including land atmosphere capping or improving current representation, in my opinion, is kind of poor at the moment, or not yet well represented. We may better exploit their role in the decadal forecast system, even though we do not dispose of sufficient observations to constrain it in a real-time decadal prediction system.
A couple comments on the stratosphere sudden warming issue went by very quickly.
Right.
There was a paper in Nature Geoscience last year by Sigmund et al. Where they actually did initialize forecast.
Right.
They did find demonstrated skill derived from warmings. If you knew they were coming, you could get some skill, predict sea ice, and surface temperature, and so on. But it's very hard to imagine how that would carry over, from year to year. One of the comments I made. The other comment, the thing that you kind of skirted was the issue of future, emission scenarios.
Right.
In particular, aerosols. I think that's an important issue. We talked about volcanoes, but kind of scenario for aerosols, anthropogenic aerosols in the future is going to be important in terms of forecasts.
Yeah. No, the point with the aerosol is the uncertainty in a future scenario. And that's, one thing is the uncertainty that we have in scenario aerosol, sulfate aerosol, and the other thing is the uncertainty in the model representation of the aerosol connected processes, like how how do we represent cloud aerosol interaction or aerosol and radiation interaction? There's a big uncertainty in model to model wise. Right.
Near term, future emission uncertainty related to anthropogenic aerosols in CN.
Yeah. Okay.
2 last quick questions. One for Wolf.
It's more of a comment to Eric's question. I think you actually need to initialize also stratosphere components. I think we have shown it for the QBO because you need to initialize the right phase of it. If you don't do it, then you do not get the performance.
Yeah.
Okay.
Yeah, the stratosphere. Yeah.
It's about going from predictability to prediction. And Martina Rice found out that when she tried to implement her knowledge with predictability coming from vegetation, by initializing the vegetation in the models, the initial shock and drift got really nasty.
Right.
So is that something that we should expect from all these additional components that we...
Well, certainly shock is an issue for sea ice as well, as I said at the beginning. And if we do not properly initialize sea ice and ocean and in a consistent way, we know that there have been studies documenting this shock. I don't know about the other components. I mean, certainly aerosols is not an initialized component. So